What if the universe is not empty, but simply choosing silence? Tonight, we'll drift into one of the deepest mysteries in science. Why, in a cosmos filled with stars, planets, and endless time, we still haven't heard a confirmed voice from beyond Earth. Welcome to Sleepy Space. If you enjoy quiet journeys through the universe, please like, subscribe, and tell us in the comments where you're listening from tonight. Tonight, before we search for aliens, before we imagine distant civilizations hiding among the stars, before we ask whether the darkness is empty or simply refusing to answer, we have to begin with a quieter and more unsettling fact. The universe, in the most literal scientific sense, does not speak in a language the human body was built to hear. Out between the planets, beyond the thin blue membrane of Earth's atmosphere, there is no air to carry pressure waves to an eardrum, no warm medium through which thunder can roll, no ocean of sound where explosions can roar the way they do in our movies and dreams. A star can tear itself apart in a supernova, releasing in moments more energy than our sun will radiate across billions of years. And yet the blast does not arrive as a scream. It arrives as light, as neutrinos, as gravitational ripples, as expanding shells of plasma, as spectral lines that must be patiently separated by instruments and mathematics. Space is not silent because nothing happens there. Space is silent because almost everything that happens there is translated into signals too ancient, too thin, too fast, too slow, or too strange for human senses to receive directly. And this is where the deeper mystery begins. Because when scientists say the universe is silent, they do not only mean that sound cannot travel through a vacuum. They mean that after decades of listening with radio telescopes, after scanning star fields, after searching for narrow-band transmissions, optical pulses, unusual infrared waste heat, suspicious stellar dimming, and other possible traces of technology, we still have no confirmed evidence that another intelligence has announced itself. Not one verified message. Not one repeating beacon. Not one unmistakable engineering signature rising above the background noise of nature. The stars shine. The galaxies drift. Pulsars tick with exquisite regularity. Quasars pour out radio waves from the hearts of distant galaxies. Black holes heat the matter around them until it glows. But none of these voices has yet formed a sentence that says clearly and without ambiguity, "We are here too." That absence is not proof that we are alone, and a careful mind should never turn a silence into a conclusion too quickly. But it is a real observation, and it has weight. The observable universe contains an almost unbearable number of stars, not merely millions or billions, but numbers so large they stop behaving like quantities and begin behaving like weather in the mind. Hundreds of billions of stars in our own Milky Way, and vast numbers of galaxies beyond it. Each galaxy a city of suns, each sun a possible center of worlds. Since the first confirmed planets around sun-like stars were found in the 1990s, astronomy has changed from wondering whether planets are rare to accepting that planets are one of the ordinary products of star formation. Dust gathers in rotating disks around young stars. Grains cling to grains. Pebbles become planetesimals. Planetesimals become worlds. And through this slow geometry of gravity, the universe builds surfaces where chemistry can wait. We now know of thousands of exoplanets, and the true number in the galaxy must be vastly larger than our catalog, because our methods mostly reveal the ones easiest to detect. Planets that cross in front of their stars from our line of sight, or tug their stars with enough gravity to make them wobble, or glow faintly enough to be separated from stellar glare. Even with these limitations, the implication is clear and profound. Earth is not surrounded by a universe that forgot how to make planets. The universe makes them constantly, lavishly, almost carelessly. And yet, from all those worlds, the sky has not returned a confirmed call. This is the wound at the center of the Fermi Paradox. The question often compressed into the simple phrase, "Where is everybody?" Enrico Fermi did not need poetry to make the question frightening. He needed only scale, time, and probability. The Milky Way is more than 10 billion years old. Our solar system formed only about 4.6 billion years ago. That leaves immense stretches of galactic history before Earth even existed. Long eras in which older stars could have formed planets. Planets could have cooled. Oceans could have gathered. Chemistry could have learned to copy itself. And intelligence, if it sometimes follows from life, could have had a head start measured not in centuries, but in millions or billions of years. If even a small number of civilizations emerged early, if even a smaller number became capable of interstellar expansion, then in simple mathematical models, the galaxy has had more than enough time to be crossed, seeded, visited, mapped, or at least marked by artifacts. This does not mean such expansion is easy, inevitable, or desirable, but it shows why the silence matters. It is not the silence of a room where no one expected guests. It is the silence of a vast old mansion in which, by many naive calculations, some light should have been on somewhere. To understand why this is not a simple contradiction, we must be precise. The search for extraterrestrial intelligence is not a single ear pressed against the entire cosmos. It is a collection of limited searches over limited times across selected frequencies with instruments that must filter out the constant interference of Earth, satellites, natural sources, thermal noise, and the strange habits of hardware. Radio SETI often looks for narrow-band signals because nature tends to produce radio emission spread over wider ranges, while technology can concentrate energy into a thin frequency channel, like a flute note held in a storm. But the radio spectrum is enormous, the sky is enormous, and time itself is enormous. A transmitter aimed at Earth for 5 minutes would be missed if no telescope was looking at the right patch of sky at the right frequency during those 5 minutes. A beacon sweeping the galaxy might not return to our direction for years. A civilization might use lasers instead of radio, or tight beams instead of broadcasts, or communication methods we have not yet imagined, just as people before Maxwell's equations had no natural intuition that invisible electromagnetic waves were passing through their walls and bodies every moment. So the silence is not total knowledge. It is knowledge bounded by method. But even bounded knowledge can be haunting. In 1977, the famous "wow" signal appeared in the records of the Big Ear radio telescope for 72 seconds, strong, narrow, and strange enough that astronomer Jerry Emin circled it and wrote that small human word of astonishment beside it. It has never repeated, and without repetition, it cannot become proof. That single event is valuable not because it proves contact, but because it demonstrates the discipline of science. A mystery is allowed to remain a mystery without being promoted into a miracle. The universe offers anomalies. The scientific mind asks them to return. Most do not. And so the silence deepens, not dramatically, but procedurally, through follow-up observations, failed confirmations, rejected false alarms, and the patient refusal to mistake desire for evidence. This restraint is part of what makes the mystery so powerful. We are not standing before an empty myth. We are standing before a measured absence. We have learned enough to know that planets are common, chemistry is widespread, and the raw materials of life are not confined to Earth. We have also learned enough to know that the leap from planet to life, from life to intelligence, from intelligence to technology, and from technology to a detectable signal may be a chain of narrow gates rather than a smooth road. The first chapter of this silence, then, is not despair. It is the recognition that the cosmos is layered against easy answers. It may be quiet because sound cannot cross vacuum. It may be quiet because signals fade with distance. It may be quiet because civilizations are rare, brief, careful, inward-looking, or separated from us by time. It may be quiet because we are listening with newborn instruments during the first moments of our technological childhood. Or, more unsettling still, it may be quiet because the conditions that allowed one species on one wet planet to build mathematics, radio telescopes, and questions about the stars are far less common than our hopes once believed. Tonight, as we begin, we do not need to decide which answer is true. We only need to hold the question steadily. Above us, the Milky Way turns with its hundreds of billions of suns. Around many of those suns, worlds move through darkness in silent orbits, some scorched, some frozen, some perhaps wrapped in clouds, oceans, and unknown weather. Our telescopes gather their faint shadows. Our equations turn brightness into radius, wobble into mass, spectrum into atmosphere. Our radio dishes listen to the cold between the stars. And for now, from all that immensity, no confirmed voice has answered. The universe is silent, not because it is simple, but because every possible explanation opens into a deeper corridor. And that is why the silence is terrifying in the gentlest way. It does not shout at us. It waits. It surrounds us. And it asks whether the only mind we know in all this darkness is ready to understand what listening truly means. Before the silence of the universe can become a mystery of life, intelligence, or hidden civilizations, it must first become a mystery of distance. Because distance is the oldest wall in astronomy. The quiet geometry that turns even a powerful signal into a fading breath long before it reaches another shore of stars. On Earth, distance feels negotiable. A voice crosses a room in a fraction of a second. A phone call crosses an ocean almost instantly. A jet aircraft can carry a person from New York to Los Angeles before the day has fully changed its color. And so the human mind, trained by landscapes small enough to walk across and technologies fast enough to collapse continents into moments, is poorly prepared for the true scale of interstellar space. The nearest star system to the Sun, Alpha Centauri, lies a little more than 4 light-years away, which sounds almost gentle until we remember what a light-year actually is. Not a unit of time, but a unit of distance. The distance light travels in 1 year at about 186,000 miles per second, or nearly 300,000 kilometers per second, the cosmic speed limit built into modern physics. A beam of light can circle Earth more than 7 times in 1 second, yet that same beam still needs more than 4 years to reach our nearest stellar neighbor. And if a civilization there sent us a message tonight, the earliest possible answer from us would not return to them for more than 8 years, even if both sides replied instantly, without hesitation, without politics, without fear, without needing to decode a single word. This is the first quiet lesson. Space does not merely separate worlds. It slows conversation until dialogue begins to resemble archaeology. Every star we look at is not simply far away, but also delayed. Sirius is seen as it was more than 8 years ago. A star 1,000 light-years away is 1,000 years out of date. A signal from the far side of the Milky Way may have begun traveling when human beings were still living in a world without agriculture, without writing, without metal, without telescopes. And only now, after crossing the dark river between spiral arms, would it be arriving at our receivers. The geometry is unforgiving because light spreads. When a transmitter sends energy equally in all directions, that energy does not travel as a narrow thread unless it is deliberately focused. It expands as the surface of an invisible sphere, and the surface area of that sphere grows with the square of the radius, according to the simple expression 4 pi r squared. This means that when the distance doubles, the same original energy is spread over 4 times as much area. When the distance increases by 10, the signal is diluted by a factor of 100. When the distance becomes 1,000 times greater, the signal is 1,000,000 times weaker. The inverse square law is not dramatic, not malicious, not mysterious. It is only geometry. But geometry on cosmic scales can feel like fate. A radio broadcast leaving Earth does not remain a loud human announcement forever. It thins outward, passing planets, asteroids, Kuiper belt objects, the heliopause, the sparse gas between stars, until what began as an organized disturbance in an antenna becomes almost indistinguishable from the cold murmur of the galaxy. And the galaxy is not a silent laboratory waiting politely for our signal. It has its own radio weather. Electrons spiraling through magnetic fields, hydrogen clouds emitting at 21 centimeters, pulsars flashing like cosmic lighthouses, Jupiter-like planets producing magnetospheric bursts, distant active galactic nuclei pouring out immense radio power from matter falling towards supermassive black holes. Against that background, a civilization trying to hear another civilization is not listening in a quiet chapel. It is trying to recognize a flute note during a storm from another continent through walls made of time. The mathematics of communication deepens the problem even further, because a signal is not useful merely because energy arrives. It must arrive with enough structure above the noise for information to be recovered. In modern information theory, the signal-to-noise ratio determines whether a message can be distinguished from randomness, and Claude Shannon's work showed that communication has limits set not by hope, but by bandwidth, power, noise, and coding. A weak signal can sometimes be recovered if it repeats, if we know where to look, if we integrate long enough, if the transmitter uses a narrow beam, if the receiver has a large collecting area, if the frequency is stable, if the interstellar medium does not distort it too badly, and if our algorithms do not discard it as interference. But each of those ifs is a gate, and a signal crossing the galaxy must pass through many gates before it becomes evidence. Even the most famous human radio leakage, the accidental outward drift of old broadcasts, radar pulses, and television carriers, is not a clean, expanding announcement that every nearby alien world could easily recognize. Much of it was never aimed at space. Much of it was low power compared with astronomical distances, and much of it spread broadly, fading rapidly. More powerful transmissions, such as planetary radar beams, can travel farther as recognizable artificial signals, but they are narrow, intermittent, and aimed at specific targets for specific reasons, not constantly sweeping every habitable planet in the Milky Way. So when we imagine Earth surrounded by a bubble of radio noise about a century in radius, we should picture not a bright, perfect sphere shouting humanity into the galaxy, but a fragile shell of uneven whispers, bright in a few directions, weak in most, already dissolving into the noise. The Milky Way itself is roughly 100,000 light-years across, so our radio presence has touched only a microscopic neighborhood around the Sun. A local bubble so small that on a map of the galaxy it would vanish beneath the tip of a needle. If another civilization is 10,000 light-years away, they cannot yet know us by our modern radio leakage, because the first century of our technological voice has not had time to reach them. If they are 1,000,000 light-years away in another galaxy, they will not receive any sign of our radio age for 1,000,000 years, and by then, the civilization that sent the signal may have changed beyond recognition, or fallen silent, or moved into forms of communication that no longer leak into space at all. Distance, therefore, changes the emotional meaning of the Fermi question. Where is everybody? Becomes less like shouting across a room and more like placing a note in a bottle, lowering it into a black ocean, and wondering why no answer has washed back before dawn. Interstellar travel is constrained by the same merciless scale. Voyager 1, launched in 1977, has entered interstellar space and become one of the most distant human-made objects. Yet, after decades of flight, it is still nowhere near another star in any ordinary human sense. At its current speed, reaching even the nearest stellar neighborhood would take tens of thousands of years. The probe is a triumph, but it is also a measuring stick for our smallness. It shows us that leaving the solar system is not the same as crossing the stars. It is only stepping from the porch of a house into the first cold field beyond the door. Proposals for interstellar probes, from fusion drives to laser-pushed light sails, try to bend the difficulty with energy, engineering, and patience. But none erases the underlying truth that mass resists acceleration. Dust becomes dangerous at high velocity, and every increase in speed demands enormous control over power and materials. Even if robotic probes someday cross to nearby stars within decades, the galaxy as a whole will remain a vast structure of delayed arrivals and ancient departures. This is why the silence of the universe may not require emptiness. It may require only scale. A civilization could be broadcasting from a world around a dim red star 3,000 light-years away, and the message may already be on its way, moving faithfully at light speed through cold dust and plasma, but it will not touch our instruments for 3,000 years. Another civilization could have received a signal from Earth centuries in the future of their own local history, long after we are gone. And they might wonder what brief species made such patterned noise and then disappeared. Somewhere, two intelligent worlds might be separated not by hostility, not by rarity, not by fear, but by the simple fact that their windows of detectability do not overlap across space-time in a way either can notice. Relativity adds a final layer of humility, because there is no universal cosmic now shared in a simple human way across all distances. Events that seem simultaneous in one frame can be ordered differently in another. And while these effects are small for slow-moving planets compared with light-speed separations, the philosophical wound remains. The universe does not present itself as one shared present moment, waiting to be experienced by everyone together. It is stitched from light cones, causal boundaries, and messages that can only move so fast. To know something exists beyond Earth, we must wait for information to arrive within our light cone. And if no information has arrived, that may tell us less about existence than about reach. The night sky, then, is not only a ceiling of stars, but a delayed archive, a library whose books are mailed across centuries, most of them still in transit, many of them too faint to read, some perhaps written in alphabets we do not yet recognize. And as we sit beneath that immense archive, our antennas listening, our equations measuring, our receivers cooling themselves against thermal noise, the first wall of silence stands before us with terrible gentleness. Not a wall made of stone, not a wall built by alien secrecy, but a wall made of radius, surface area, signal loss, finite light speed, and the enormous patience demanded by a galaxy. The universe may be full of places, but places are not neighbors merely because they exist. A star can shine in the same galaxy and still be unreachable by conversation. A planet can be alive and still be hidden behind distance so vast that its story arrives too late. A civilization can speak and still be unheard. And so, before we imagine darker answers, before we ask whether life is rare or intelligence is brief, or everyone is hiding in a cosmic forest, we must sit with the first and simplest explanation. The universe is silent because it is large beyond the scale for which the human heart was designed, and every possible voice must cross that largeness, one fading wave at a time. If distance is the first wall that quiets the universe, then time is the second wall, and it is stranger, softer, and in some ways more unforgiving, because distance only tells us that a signal must travel far, while time tells us that the sender and the listener may never be awake in the same era of the cosmos. We often imagine the search for extraterrestrial intelligence as if all civilizations, if they exist, are standing under the same night sky at the same moment, each one deciding whether to speak or remain silent. But astronomy has slowly taught us that the universe does not offer a single shared present in the ordinary human sense. Every star is seen by delay. Every world is observed through an interval. Every possible signal arrives not from where a civilization is, but from where it was when the light or radio wave began its journey. A planet 100 light-years away is not being seen as it is tonight. It is being seen as it was a century ago, when people on Earth were only beginning to understand radio as a planetary technology. A world 10,000 light-years away is visible to us as it was before the rise of many human civilizations, before modern science, before telescopes, before electricity, and perhaps before anyone on that distant world had either appeared or vanished. Time turns the galaxy into a vast archive of mismatched moments, and the silence of the sky may not mean no one has ever spoken. It may mean that their voices crossed our region of space before we had ears, or will arrive long after the instruments we now trust have become museum pieces, dust, or something beyond recognition. The Milky Way is more than 13 billion years old, and our solar system is only about 4.6 billion years old, which means that for billions of years before Earth existed, older stars had already formed, died, enriched space with heavier elements, and given birth to later generations of planets. The carbon in our cells, the oxygen in our lungs, the iron in our blood, and the silicon in our machines were not present in the earliest universe in useful abundance. They were forged inside stars and scattered by stellar death. So the possibility of life depends not only on planets, but on cosmic chemical history. There had to be enough time for the universe to make the elements of biology, enough time for rocky planets to assemble, enough time for stable stars to shine, enough time for chemistry to become patient. Yet once those ingredients existed, there was still no guarantee that intelligence would appear quickly, or that technology would last long once it did. Earth is a cautionary clock. Our planet formed about 4.54 billion years ago. Life seems to have emerged relatively early in Earth's history, though the exact timeline remains an area of active research. But for most of that immense span, life was microbial, small, persistent, invisible to any distant telescope except through atmospheric chemistry. Single-celled organisms shaped the planet for billions of years without ever producing radio, metallurgy, mathematics, or a signal aimed at the stars. Complex multicellular life came much later. Animals with hard parts became abundant in the Cambrian period, roughly 500 million years ago. Dinosaurs ruled land ecosystems for more than 100 million years and never built an observatory. Mammals diversified after the asteroid impact 66 million years ago. The human lineage split from the lineage leading to chimpanzees only several million years ago. Anatomically modern humans appeared only a few 100,000 years ago. Agriculture is roughly 10,000 years old. Writing is only several thousand years old. Industrial technology is only a few centuries old. Radio, the technology that first made Earth even faintly detectable as a communicating world, is barely older than a human lifetime extended across generations. When set against Earth's full history, our technological phase is not a chapter. It is a spark at the edge of the final page. This compression matters profoundly because if another planet followed a similar pattern, it might be alive for billions of years and yet detectable as technological for only a tiny fraction of that time. A civilization could bloom, build antennas, send structured signals, and then change technologies or fade before its radio waves had crossed even a modest portion of the galaxy. This is why the Drake equation, proposed by Frank Drake in 1961, includes a factor often treated with quiet unease. The length of time a technological civilization releases signals that can be detected across interstellar distances. This variable, commonly written as L, is not simply a number. It is the duration of visibility, the length of the lantern's flame. If L is long, thousands or millions of years, then even rare civilizations might overlap enough for discovery. If L is short, perhaps only centuries or millennia, then the galaxy can contain many intelligent species that still never hear one another, because their brief, detectable windows open and close like fireflies, blinking in different valleys on different nights. The equation does not solve the mystery, because we do not yet know the values of its most important biological and cultural terms. But it disciplines the imagination by showing that contact is not determined only by how often civilizations arise. It is determined by whether their eras intersect. Time also changes the meaning of progress. A civilization may not remain radio loud. Early human technology leaked energy wastefully into space through broad broadcasts and powerful radar. But as communication systems improve, they often become more directed, more efficient, more compressed, more fiber-based, more satellite-linked, less like shouting into a valley and more like whispering through a wire. If an advanced society becomes technologically mature, it might not grow louder from the outside. It might become quieter. Its communications could be narrow beams between planets, optical links, encrypted local networks, or methods not yet available to our physics or engineering. From far away, its loud adolescence might last only a short time before being replaced by a quieter adulthood. If that pattern is common, then the universe may be filled not with civilizations that never existed, but with civilizations whose noisy phases are so brief that we rarely catch them. The historical irony is delicate and almost painful. By the time a society becomes powerful enough to search the stars, it may also be learning how not to spill its voice carelessly into space. There is another temporal difficulty hidden in the idea of reply. Suppose we detect a signal tomorrow from a star system 1,000 light-years away. The civilization that sent it transmitted the signal 1,000 years ago. If we answer immediately, our reply will arrive there 1,000 years from now. The original senders may be gone. Their language may have changed. Their planet may have transformed. Their descendants, if they exist, may no longer remember the project, or may no longer use the technology required to receive our response. Communication across the galaxy is therefore not conversation as humans understand it. It is closer to the exchange of monuments. Each message is carved into electromagnetic stone and thrown across time, hoping that someone in a later age is still standing where the address says they should be. This creates a profound possibility. Two civilizations could both be curious, both peaceful, both listening, and still miss one another because curiosity does not abolish delay. They might each spend centuries scanning the sky during quiet intervals, separated by signals still in transit, each concluding that the other is absent. The silence becomes not a verdict on existence, but a failure of synchronization. Astrobiology adds still more texture to this misalignment. Planets orbit different kinds of stars with different lifetimes. Massive blue stars burn bright and die quickly, usually too quickly to provide the long stability associated with complex biological evolution. Sun-like stars offer billions of years of steady light. Red dwarfs can live for trillions of years, raising the possibility that much of the universe's future habitability may lie far ahead, not behind us. Some researchers have suggested that, in a broad cosmic sense, we may be early. The universe is 13.8 billion years old, but star formation and planetary evolution may continue for immense spans, especially around long-lived, low-mass stars. If that is true, the present silence might not mean life has failed to appear elsewhere. It could mean that much of life's grand history has not happened yet. We might be among the early technological voices, not the late ones. That possibility is less frightening than extinction, but more solemn, because it would make humanity not merely a listener, but perhaps one of the first fragile examples of matter becoming aware of the stars. And yet, the opposite possibility also remains. Many civilizations may have appeared long before us and disappeared before our instruments existed. Their radio shells, if they had any, may already have passed Earth when our planet had no listeners. Their ruins, if they left any, may orbit stars too far away for our telescopes to resolve. Their lessons, if they learned them, are not automatically delivered to younger worlds. Time does not preserve every voice for every future ear. It lets light travel, but it does not promise understanding. This is the deeper terror and beauty of the temporal answer. The universe may be less like an empty theater and more like a theater where plays are performed in different centuries, with the audience arriving after the actors have gone home or before the stage has been built. We listen during our narrow century of radio astronomy, with instruments still young, methods still developing, and archives still incomplete. And we are tempted to measure the whole cosmic drama by the silence inside our brief observing window. A humbler view sees our search as the first careful opening of an eye, not the final survey of reality. Still, the silence is real for us, here and now. No confirmed civilization has entered our time. No signal has crossed into our present with enough clarity to survive scientific doubt. Above us, the stars carry their delayed light across the sky, each one a memory, each one a possible world seen out of date, each one reminding us that the galaxy is not only wide, but old, and that old things do not arrange themselves for young listeners. Perhaps someone spoke too early. Perhaps someone will speak too late. Perhaps the answer is already traveling toward us, patient and cold, needing another 1,000 years to arrive. And so, the silence of the universe may be the silence of missed appointments on a scale so vast that even longing cannot shorten it. Civilizations rising like candles in separate rooms of time, burning briefly, beautifully, and never knowing that somewhere else, behind another wall of years, another flame was waiting. The discovery that planets are common should have made the universe feel less lonely. And in one sense, it did, because the old picture of our solar system as a rare arrangement of worlds around an ordinary star has been replaced by something far more abundant and more mysterious. Stars, it turns out, are very good at making planets. Around young suns, disks of gas and dust flatten into rotating nurseries, and inside those disks, tiny grains collide, cling, fracture, settle, and gather again, until gravity begins its patient work and the architecture of a planetary system slowly emerges from what was once only a dusty halo. This process is no longer a speculation drawn from philosophy. It is seen in protoplanetary disks, measured through exoplanet surveys, inferred from transits and radial velocities, and folded into the modern understanding of star formation itself. Yet the more planets we find, the more carefully we have to distinguish between a planet that exists, a planet that is warm, a planet that has water, a planet that is chemically active, and a planet that can remain stable long enough for life to become complex. Because the silence of the universe may not be explained by a lack of worlds, but by the difficulty of keeping a world gentle for billions of years. The phrase habitable zone sounds almost comforting, as if astronomy has drawn a soft green ring around every star and placed a quiet promise inside it. But scientifically, it is only a first approximation, a calculation based on stellar luminosity, orbital distance, atmospheric assumptions, and the possibility that liquid water could exist on a rocky surface. At the most basic mathematical level, the energy received by a planet falls with the square of its distance from the star. So a world twice as far away receives 1/4 of the stellar flux. And from that simple inverse square geometry, we can begin to estimate equilibrium temperatures, greenhouse needs, ice lines, and the rough region where water might neither freeze permanently nor boil away entirely. But the real climate of a planet is not a single equation. It is an evolving system of atmosphere, clouds, oceans, land distribution, rotation rate, axial tilt, volcanic gases, surface reflectivity, stellar spectrum, and feedback loops. Venus and Mars are the quiet warnings on either side of Earth. Venus may once have had conditions more temperate than it has now, but today, its thick carbon dioxide atmosphere, sulfuric acid clouds, and runaway greenhouse state make its surface hot enough to melt lead. Mars has river valleys, lake beds, minerals shaped by water, and polar ice, but its small size, thin atmosphere, and long-term atmospheric loss have left its surface cold, dry, and exposed. Both worlds orbit near Earth in the same solar system, born from the same broad family of materials, and yet neither became a second Earth. That simple comparison should make us cautious. It shows that location is not destiny. A planet can be in or near the right region and still lose the long argument between geology, atmosphere, radiation, and time. Earth's unusual value may lie not in one miraculous property, but in a suite of interacting conditions that stayed favorable for nearly the entire history of life. Its distance from the Sun allowed stable liquid water under the right atmospheric pressure. Its mass was large enough to hold an atmosphere, but not so large that it became a mini Neptune wrapped in a deep hydrogen envelope. Its molten interior helped power volcanism, and for much of its history, plate tectonics, which may have played a central role in regulating carbon dioxide through the carbon silicate cycle. Volcanoes release carbon into the atmosphere. Weathering removes it into rocks and oceans. Subduction recycles it into the mantle. And over millions of years, this slow geochemical breathing can moderate climate as the sun gradually brightens. This does not mean plate tectonics is proven to be absolutely necessary for life everywhere. But for Earth, it appears deeply tied to long-term habitability, nutrient cycling, continental growth, and climate stability. Earth also has a global magnetic field generated by motion in its liquid outer core. And while scientists continue to study how essential such protection is for different planetary environments, the magnetosphere has helped shape how the solar wind interacts with our atmosphere, reducing some forms of atmospheric stripping and creating a shielded electromagnetic environment that differs sharply from Mars. Earth's large moon adds another layer of nuance. It raises tides, records early impacts, and likely contributes to stabilizing Earth's obliquity over long timescales, helping prevent extreme swings in axial tilt that could drive severe climate instability, though the exact importance of this factor in habitability remains debated. Jupiter, too, is often described as a protector, sweeping up or redirecting comets and asteroids. But the truth is more complex, because a giant planet can both reduce and increase impact rates depending on the architecture of the system. Still, its presence shaped the gravitational environment in which Earth evolved, sculpting asteroid belts, resonances, and the delivery history of volatile materials. Even the early violence of the solar system may have mattered, because impacts delivered and removed material, sterilized and reshaped surfaces, and may have helped establish the inventory of water and carbon compounds that later biology would use. A world that is too peaceful might lack crucial ingredients. A world too violent might never allow chemistry to settle. Habitability, then, is not a static label, but a history, a long negotiation between chance and regulation. When astronomers describe potentially habitable exoplanets, they are usually working with incomplete information. Radius, orbital period, stellar type, sometimes mass, sometimes atmospheric hints, often very little else. A rocky planet around a red dwarf may look promising because red dwarfs are abundant and long-lived, but the habitable zone around such a cool star lies close in, where tidal locking may cause one hemisphere to face the star continuously, while the other remains in endless night. Climate models suggest that a dense enough atmosphere or ocean could transport heat and soften that contrast, so tidal locking is not automatically fatal. But close-in planets around active red dwarfs may also endure strong flares, ultraviolet radiation, and stellar winds capable of eroding atmospheres, especially early in the star's life. A planet around a hotter, more massive star may receive abundant light, but such stars live shorter lives, possibly leaving too little time for complex evolution. A planet around a sun-like star may have a more familiar energy source, but its orbit, composition, volatile history, and internal heat still decide whether it becomes a living world, a sterile desert, an ice-covered ocean, or a gas-rich super-Earth with no accessible surface at all. This is where the rare Earth idea enters, not as a settled verdict, but as a useful caution against assuming that a large number of planets automatically becomes a large number of technological civilizations. Simple life may require one set of conditions. Complex life may require another. Intelligence capable of astronomy may require yet another, much narrower path. On Earth, life seems to have appeared relatively early, but complex life took billions of years, and that delay may hint that microbial worlds could be common, while worlds with forests, animals, eyes, nervous systems, and tool-making species remain much rarer. If this is true, the galaxy may not be empty at the level of chemistry or even biology. It may be full of quiet microbial oceans, warm subsurface seas, frozen moons with hydrothermal vents beneath ice, planets with atmospheric disequilibrium but no minds, and living worlds that never become loud. The silence would not come from cosmic sterility, but from cosmic subtlety. From far away, Earth itself would have been silent for almost all of its living history. For billions of years, it had microbes, oceans, storms, continents forming and breaking apart, oxygen slowly rising, mass extinctions carving biological possibility into new forms. Yet no radio towers, no city lights, no deliberate messages, no machines measuring other stars. If an observer had watched Earth across most of its past, they might have seen a biosphere, but not a civilization. That distinction matters because the Fermi question is not simply asking why there are no planets, or no water, or no carbon. It is asking why there is no detectable intelligence. And the path from a wet rock to a radio telescope may be one of the narrowest paths nature ever found. Still, we should not let caution harden into certainty. Earth may be unusual in some ways and ordinary in others. Some conditions we once thought essential may turn out to be only one successful arrangement among many. life may adapt to environments that seem hostile from a human perspective. Subsurface oceans may support ecosystems without sunlight. Planets, unlike Earth, may sustain stable climates through mechanisms we have not yet fully modeled. The history of science repeatedly warns against mistaking local experience for universal law. And yet, the growing catalog of worlds has not made the silence disappear. It has sharpened it. Every new planet is both a promise and a question. Every rocky world in a temperate orbit says that the stage may exist, while every unanswered sky reminds us that a stage is not a play, a sea is not a cell, and a cell is not a civilization. Perhaps the universe is crowded with planets, but only rarely does one become a long-lived cradle. Perhaps there are countless cradles, but most rock gently in darkness, raising only simple life beneath clouds no one will name. Or perhaps, somewhere beyond the reach of our current instruments, other Earths are turning under other moons, their oceans breathing under alien constellations, their atmospheres waiting to be read by telescopes not yet built. For now, Earth remains the only confirmed living world, not necessarily because it is the only one, but because it is the only one close enough for us to know intimately. And that intimacy may be the most humbling part of the silence. The blue planet beneath us is not just one data point in a catalog. It is the only place where the universe has unquestionably become aware of planets, stars, chemistry, and silence itself. In the dark, this makes Earth feel less like an ordinary stone and more like a lamp kept burning in a very large house, while beyond its window, countless other rooms may exist, some empty, some sleeping, some perhaps alive, but so far none with a light bright enough for us to see. Even if the galaxy is crowded with planets, even if many of those planets have oceans, atmospheres, minerals, lightning, tides, volcanic heat, and long, quiet ages beneath patient stars, the silence of the universe still has to pass through one of the deepest questions science has ever asked. How does matter that is not alive become matter that remembers, copies, competes, adapts, and slowly begins to behave as if the universe has taught it a private grammar? This first step, often called abiogenesis, is not the same as evolution, and that distinction matters, because evolution explains how life changes after self-replicating systems already exist, while abiogenesis asks how such systems appeared in the first place. Charles Darwin gave biology a mechanism for the transformation of living forms through variation and natural selection. But he did not fully solve the origin of the first living chemistry. And modern science, with all its laboratories, spectrometers, genetic sequencing, planetary missions, and computer models, still approaches that threshold with extraordinary care. We know that life on Earth is built from chemistry, not magic. We know that carbon is unusually good at forming complex structures because it can bond with itself and with many other elements in flexible chains, rings, and branching architectures. We know that water is a remarkable solvent because its polarity allows it to dissolve ions, shape proteins, mediate reactions, and create environments where molecules can meet and rearrange. We know that energy gradients matter because life is not merely a collection of molecules, but an organized flow of energy through matter, a way of maintaining local order by drawing usable energy from the environment and releasing waste heat back into the larger universe. But knowing the ingredients and principles is not the same as knowing how the first living system assembled itself. A kitchen full of flour, salt, water, and heat is not yet bread. A planet full of carbon, nitrogen, phosphorus, iron, sulfur, sunlight, hydrothermal vents, clays, tides, and impacts is not yet alive. Somewhere between chemistry and biology, molecules had to become organized enough to store information, copy that information with imperfect fidelity, and pass through selection, because without inheritance, there is no Darwinian evolution, and without variation, there is no open-ended adaptation. The central mystery is not whether organic molecules can form. Many can. The famous Miller-Urey experiment in 1953 showed that amino acids could arise from simple gases under energetic conditions meant to approximate some early Earth environments, though our understanding of the early atmosphere has changed since then, and the experiment is now best viewed not as a complete origin story, but as a powerful demonstration that prebiotic chemistry can move in biologically interesting directions. Since then, amino acids and other organic compounds have been found in meteorites. Complex carbon chemistry has been observed in interstellar clouds, and planetary science has shown that the raw materials of biology are not confined to Earth. Comets and asteroids can carry water and organics. Titan has lakes of methane and ethane under an orange haze of complex chemistry. Enceladus sprays plumes of water vapor and organic molecules from a subsurface ocean into space. Europa may hide a deep ocean beneath its ice, warmed by tidal forces from Jupiter. Mars preserves minerals that formed in the presence of ancient water. The universe, in other words, does not seem poor in ingredients. It seems rich, almost lavish, in the chemical alphabet from which life might be written. And yet an alphabet is not a book. The letters may be everywhere, while the first sentence remains rare. One of the most influential ideas in origin of life research is the RNA world hypothesis, which suggests that before modern cells used DNA to store genetic information and proteins to perform most catalytic work, earlier life, or proto-life, may have relied on RNA, a molecule capable both of carrying information and, in some cases, catalyzing reactions. This makes RNA conceptually attractive because it narrows the chicken and egg problem of which came first, genes or enzymes. But the RNA world is not a finished solution. Researchers still investigate how ribonucleotides could have formed under plausible early Earth conditions, how they could have polymerized into longer strands, how those strands could have copied themselves, and how such fragile molecules could persist in environments that also break molecules apart. Other models shift attention toward metabolism first, imagining networks of chemical reactions near hydrothermal vents, where mineral surfaces, temperature gradients, alkaline fluids, and proton differences across tiny natural pores might have provided a setting for early energy conversion before genetic molecules fully took over. Still other hypotheses emphasize lipid membranes, because life as we know it requires boundaries. A cell is not just chemistry scattered through an ocean, but chemistry held together inside a compartment, where useful molecules are concentrated, reactions become more likely, and a primitive inside can begin to differ from the outside. Fatty acids can form vesicles under certain conditions, creating tiny bubbles that grow, divide, and encapsulate molecules, hinting at how protocells might have emerged before modern cellular machinery. Mineral surface models suggest that clays or metal sulfides could have organized and catalyzed reactions, offering scaffolds on which early chemistry became less random. No single model has yet won complete consensus, and that uncertainty is not a weakness of science. It is the honest shape of a frontier. The origin of life may have involved several of these processes together. Not one elegant step, but a braided pathway. Organic synthesis in the atmosphere or space, concentration in drying ponds or volcanic pools, catalytic surfaces, wet-dry cycles that help polymers form, protective compartments, energy gradients, and selection operating gradually on chemical systems before anything existed that we would confidently call a cell. The difficulty is that early Earth was a restless, changing planet, and the oldest evidence has been heavily altered by geology. Rocks are recycled by plate tectonics, transformed by heat and pressure, eroded, buried, and rewritten. Life itself, once established, devoured or obscured many traces of the prebiotic world that came before it. We are trying to reconstruct the first candle from the smoke left after billions of years of weather. This is why astrobiology must be humble when it speaks about probability. The fact that life appeared on Earth relatively early after the planet became habitable may suggest that life can arise readily under favorable conditions. But with only one confirmed example, we cannot know whether Earth was typical or astonishingly lucky. A sample size of 1 is a lantern, not a map. It illuminates what happened here, but it cannot yet reveal how often it happens elsewhere. If abiogenesis is easy, then microbial life may be scattered through the galaxy, quiet and durable, living in oceans under ice, in deep crustal rocks, in warm ponds, in hydrothermal systems, perhaps even beneath the surfaces of worlds that look dead from orbit. If abiogenesis is difficult, then the universe may contain countless planets with all the right ingredients, all the right temperatures, and all the right chemistry. Yet no living process ever crosses the threshold into self-sustaining evolution. This possibility gives the silence a different tone. It is not the silence of empty space alone, but the silence of almost life, of worlds that came close but never awakened. Imagine an ocean under a dim star, warmed by black smokers on the seafloor, rich with carbon compounds, iron, sulfur, and mineral surfaces, stirred for hundreds of millions of years by tides and impacts, yet never producing a system that can copy itself well enough for natural selection to begin. Imagine a planet where amino acids form and break, where membranes appear and dissolve, where chemical cycles flicker and fail, where the first step is attempted endlessly by chance and thermodynamics, but never locked into heredity. Such a world would be chemically fascinating, perhaps beautiful beyond measure, but from the perspective of SETI, it would remain silent forever. And even if life does begin, the first life is not a voice. Microbes do not build transmitters. A planet can be alive for billions of years and still be invisible as intelligence. Earth itself spent most of its living history in this quiet state. Its oceans were active. Its microbes transformed the atmosphere. Cyanobacteria eventually filled the air with oxygen. And still, no mind looked up and asked whether anyone else was listening. From across interstellar distances, early Earth might have shown atmospheric clues, perhaps methane in disequilibrium, later oxygen and ozone, but not intention, no beacon, no mathematics, no signal shaped by curiosity. This is why the origin of life is so central to the silence of the universe. It is the first gate, and every later gate depends on it. Without abiogenesis, there is no evolution. Without evolution, no complex organisms. Without complex organisms, no nervous systems. Without nervous systems, no intelligence. Without intelligence, no technology. Without technology, no detectable civilization. The entire Fermi question rests on chemistry becoming biology at least once, and perhaps many times, but we do not yet know whether that transformation is common like rain or rare like a perfect eclipse. The silence above us may therefore be holding a secret that is neither comforting nor cruel, only immense. The universe may have built billions of stages and scattered them with the props of life, but the first actor may step onto the stage only rarely. Or perhaps actors are everywhere, but most never speak loudly enough for the upper balconies of the galaxy to hear. For now, Earth remains the one confirmed place where the first step happened, where carbon chemistry crossed into inheritance, where inheritance became evolution, where evolution became awareness, and where awareness now turns back toward the dark and wonders whether that first step was ordinary or nearly impossible. In the quiet of night, this makes every living cell feel ancient and improbable, a small, warm refusal of disorder, a microscopic archive of a beginning we have not yet learned to recreate fully or find elsewhere. The universe may be rich with planets, but until we understand how non-living matter first learned to become alive, the silence will keep its first and deepest door closed. If life begins somewhere beyond Earth, under another sky, in another ocean, around another star, it is tempting to imagine that time alone will eventually guide it toward intelligence, toward tools, toward mathematics, toward radio telescopes turning upward in the dark. But this temptation comes from a very human misunderstanding of evolution. Because evolution is not a staircase rising patiently toward civilization. And it is not a cosmic curriculum with technology waiting at the final lesson. Evolution is a local process, blind in the ordinary scientific sense, shaped by variation, heredity, selection, drift, constraint, accident, and environment. And it rewards whatever works well enough for survival and reproduction in a particular place at a particular time, not whatever will someday decode the spectrum of a distant star. A bacterium spreading through warm rock is not less successful than an astronomer because it does not know the Milky Way exists. A fern opening in mist, a jellyfish pulsing through dim water, a trilobite crossing an ancient seafloor, a dinosaur ruling a continent for millions of years. Each is part of life's vast experiment, and none of them is moving toward us as a goal. This is why the silence of the universe becomes deeper after the origin of life, not shallower. Because even if biology appears often, the path from biology to detectable intelligence may be narrow, contingent, and full of gates that no planet is required to pass. On Earth, life existed for roughly 3 billion years before complex multicellular organisms became widespread. And for most of that immense span, the planet was alive but not technological, active but not communicative, transforming oceans and atmosphere through microbial metabolism while producing nothing that another civilization would recognize as a mind calling across space. The oxygenation of Earth's atmosphere, driven largely by photosynthetic microorganisms, was one of the most important planetary transformations in our history. But it was not a message. It changed chemistry, climate, and biological possibility. Yet it did not build an antenna. Even after animals emerged, nervous systems did not automatically become human-like intelligence. Natural selection repeatedly produced movement, senses, camouflage, shells, venom, wings, jaws, flowers, social colonies, echolocation, and countless strategies for being alive. But only once, as far as we know, did it produce a species capable of deriving Maxwell's equations, splitting the electromagnetic spectrum into communication bands, and wondering why no one else is transmitting. That once may be meaningful, or it may be a sampling illusion created by the fact that we have only one planet to study. But it is enough to make caution necessary. Intelligence, even on Earth, is not a single thing. Crows can solve puzzles and remember faces. Octopuses can manipulate objects, explore with flexible arms, and show striking behavioral complexity, despite having an evolutionary history very distant from ours. Dolphins and whales live in acoustic worlds of memory, social bonds, and long-range sound moving through water. Elephants remember landscapes and mourn their dead. Primates use tools, alliances, gestures, and social learning. Ant colonies and termite mounds produce collective structures that appear almost architectural without requiring human-style consciousness. These forms of cognition remind us that mind is not one mountain with humanity at the summit. It is an archipelago of abilities, each island shaped by body plan, ecology, sensory world, and evolutionary history. But none of these intelligences, rich as they are, has produced radio. That difference is not simply about brain size. It is about the coupling of brain, body, environment, and culture. To build technology that can be detected from another star, a species needs more than awareness. It needs manipulators precise enough to shape matter, social systems capable of preserving knowledge, communication flexible enough to transmit abstractions, access to usable energy, and an environment where fire, metallurgy, chemistry, and eventually electronics can become practical. A whale may have an inner life of immense depth, but living in the ocean makes fire inaccessible. Without fire, many paths to metallurgy close. Without metallurgy, the route to wires, generators, vacuum tubes, semiconductors, and radio transmitters becomes very hard. Perhaps not absolutely impossible under all imaginable circumstances, but profoundly constrained by physics and materials. An octopus has dexterous limbs and problem-solving ability, but it has a short lifespan, mostly solitary habits, and an aquatic environment that makes cumulative technological culture difficult along the path humans followed. A crow has intelligence, but not hands suited to high-precision manufacturing. A species might be thoughtful under ice, musical in a methane sea, or socially brilliant in a dense atmosphere, yet never develop the chain of material control required to leave a technosignature. This is where the geometry of the body becomes part of the geometry of silence. A brain does not build a civilization by itself. It must act through limbs, tools, shared symbols, stable memory, and external storage. Human beings became technological not because intelligence appeared in isolation, but because many conditions converged. Upright posture freed the hands. Opposable thumbs gave fine manipulation. Social living rewarded communication and cooperation. Long childhoods allowed learning. Fire changed diet and energy use. Language compressed experience into transmissible form, and culture began to accumulate discoveries faster than genes could evolve. The difference between a clever animal and a technological civilization may lie in cumulative culture, the ratchet-like ability to preserve small improvements so that each generation does not begin again from zero. A snowflake becomes a sharper snowflake. A spear becomes a bow. A kiln becomes metallurgy. Metallurgy becomes machines. Machines become instruments. Instruments become science. And science becomes a self-correcting method powerful enough to reveal laws no unaided sense could discover. This chain is fragile because each link depends on the previous one and on a world where materials are accessible. A planet entirely covered by deep ocean might host life and intelligence, but without exposed land, concentrated ores, dry combustion, and stable surfaces for building, the technological route might be radically different or blocked. A high-gravity super-Earth could make flight and rocketry far more difficult, increasing the energy cost of reaching orbit because orbital velocity scales with the planet's mass and radius, and deeper gravity wells demand more powerful propulsion. A world with constant storms, intense radiation, or unstable climate might produce adaptive intelligence without long-lived institutions. A tidally locked planet around a red dwarf might have habitable regions near a twilight zone, but its ecology, weather, and stellar environment could shape cognition in ways we cannot easily predict. None of these scenarios proves intelligence will not arise. They simply show that life does not automatically become a technological observer. Historical contingency deepens the point. Stephen Jay Gould famously emphasized that if the tape of life were replayed, the outcome might differ dramatically because evolution depends on chance events, extinctions, environmental shifts, and tiny advantages amplified over time. The asteroid impact 66 million years ago did not happen in order to clear space for mammals. It was a catastrophic event whose aftermath opened ecological possibilities that eventually contributed to the rise of primates. Had that impact missed Earth? Had climate changed differently? Had certain lineages failed or flourished? The planet might still be alive and complex today, but without humans or anything like us. Intelligence may be convergent in some broad forms because eyes, wings, echolocation, and sociality have evolved multiple times when environments favor them. But human-level technological intelligence has not obviously repeated in the same way. The record shows many clever solutions, not a guarantee of civilization. And this has enormous consequences for the Fermi question. If life is common but mostly microbial, the galaxy remains quiet. If complex life is common but mostly non-technological, the galaxy remains quiet. If intelligence is common but embodied in forms that sing, hunt, remember, dream, and navigate without industry, the galaxy remains quiet. If technology appears but does not cross into astronomy, electricity, or long-range signaling, the galaxy remains quiet. The silence above us could therefore be filled with unseen life that never becomes audible. It could contain living worlds with forests under alien suns, reef-like structures beneath ice, migrating creatures in thick atmospheres, nervous systems unlike ours moving through chemical senses we would barely recognize, and still no signal would reach a radio dish on Earth. In that sense, the search for extraterrestrial intelligence is not only a search for life, it is a search for a very specific kind of life that has entered into partnership with mathematics, energy, and machines. This partnership is recent even here. For nearly all of human history, we were intelligent, but not detectable across interstellar distances. Our ancestors tracked animals, painted caves, buried their dead, read weather, told stories beside fire, and looked at stars without becoming a radio source. The human mind existed long before the technological footprint. Intelligence was present, but the galaxy could not hear it. This distinction matters because it means that even if another planet has minds, those minds may live in a long pre-technological dawn or may choose paths that do not produce detectable leakage, or may never need the machinery we associate with progress. Progress itself is a cultural word, not a law of biology. Evolution has no obligation to produce telescopes. It produces fit organisms, and sometimes, under very specific conditions, fit organisms become curious enough and capable enough to build instruments that extend their senses beyond their world. The terrifying gentleness of this idea is that the universe may not be barren. It may be quietly alive in ways that never become visible to our searches. We may be listening not for life in general, but for the rare moment when life turns into technology, and technology turns outward, and outwardness becomes strong enough to cross the gulf between stars. If that moment is rare, brief, or dependent on a chain of accidents, then the silence is no longer surprising. It is the expected hush of a galaxy where biology often stays local, where minds may bloom without machines, and where only a few worlds, perhaps very few, ever build a voice loud enough to enter the night. And so, as we drift deeper into the question, the universe becomes less like an empty room and more like a dark forest filled with sleeping seeds, quiet animals, hidden rivers, and perhaps thoughts that never become radio waves, reminding us that intelligence is not the destination of evolution, but one fragile branch among many, and that the branch capable of asking where everyone is may be rarer than the stars made us hope. If life can begin, and if intelligence can sometimes rise from life, and if a thinking species can occasionally discover fire, tools, language, mathematics, electricity, and the faint radio pathways between the stars, then the silence of the universe still leads us toward one of the most elegant and unsettling ideas in the entire discussion of cosmic loneliness. Somewhere between dead matter and a civilization capable of lasting across galactic time, there may be a barrier so difficult to cross that almost no one passes it. This idea is often called the Great Filter, and its power comes from the way it gathers many uncertainties into a single, quiet question. If the universe has had billions of years, and if planets are common, and if chemistry is rich, and if some worlds are old enough to have reached technology long before Earth, then why do we not see the result shining in the sky? The Great Filter is not one specific wall that science has already identified. It is a framework, a way of thinking about probabilities across a long chain of transitions, each one necessary for a visible civilization to appear. The chain begins with a suitable star, a stable planet, and the right materials. But then it must move through the origin of life, the development of heredity, the emergence of complex cells, the rise of multicellular organisms, the evolution of nervous systems, the appearance of intelligence, the formation of culture, the invention of technology, the ability to communicate across space, and finally, the endurance required to remain detectable for long enough that another young species might notice. If any one of those steps is extremely unlikely, then the silence becomes less mysterious, because most worlds would stop before they ever became loud. The frightening part is that we do not yet know where the hardest step lies. It may be behind us, in the deep past, hidden among events so ancient that Earth's rocks have almost erased their footprints. Perhaps the first self-replicating chemistry is nearly impossible, and Earth happened to win a cosmic lottery so rare that most habitable planets remain forever lifeless, even with oceans and carbon and energy. Perhaps simple life appears fairly often, but the transition to complex cells, especially eukaryotic cells with internal structures and energy-rich mitochondria, is extraordinarily difficult, requiring a rare symbiotic event that does not easily repeat. Perhaps multicellular life is the filter, because cells must not only survive, but cooperate, specialize, communicate, suppress internal conflict, and build bodies across developmental time. Perhaps intelligence itself is the narrow gate, because many forms of life can be beautifully adapted without ever needing abstract reasoning, cumulative culture, or symbolic language. If the Great Filter is mostly behind us, then the silence of the universe, though lonely, may contain a strange kind of hope. It would mean that humanity has already crossed one or more of the rarest thresholds in nature. It would mean that the difficult miracle happened early, perhaps in a warm pond, a hydrothermal vent, a mineral pore, or inside the long chemical twilight of young Earth, and that our responsibility now is not to assume the universe is empty, but to recognize that a living, thinking planet may be more precious than any ancient empire ever imagined. But the same idea has a darker mirror. The filter may not be behind us, it may be ahead. And if it is ahead, then the silence becomes less like an empty room and more like a warning written in the absence of older voices. A technological civilization is a very young kind of phenomenon, at least in the only example we know. Humanity spent hundreds of thousands of years as an intelligent species before becoming industrial. And then, only a few centuries were needed to move from steam engines to radio, from radio to rockets, from rockets to computers, from computers to planetary-scale networks, and tools powerful enough to alter the conditions of our own world. This acceleration is not automatically tragic, but it is structurally dangerous in a broad evolutionary sense, because natural selection did not prepare human judgment for powers that operate across centuries, biospheres, and global systems. A species can become technically capable before it becomes politically wise, ecologically patient, or socially coordinated enough to manage the consequences of its own inventions. The Great Filter, in this future-facing form, does not need to be a single dramatic catastrophe. It could be a family of pressures that repeatedly challenge civilizations after they discover high technology. Environmental instability, energy transition, long-term resource management, social fragmentation, uncontrolled competition, poorly governed transformative tools, or the simple difficulty of maintaining cooperation at planetary scale when short-term incentives pull in different directions. These possibilities should be discussed carefully, not as prophecies and not as cinematic doom, but as systemic risks. Because the scientific point is not that every civilization must destroy itself, but that even a modest probability of failure, repeated across many worlds and many technological histories, could greatly reduce the number of long-lived civilizations visible in the galaxy. In probability terms, if each step in the chain has a survival fraction, the final number is the product of all those fractions, and multiplication can be merciless. A step that seems only moderately difficult becomes devastating when combined with many other difficult steps. This is why the Drake equation and the Great Filter speak to each other so naturally. The Drake equation asks how many communicating civilizations might exist now. The Great Filter asks which terms in that chain might be small enough to make the answer nearly zero. It may be that the term for life is small. It may be that the term for intelligence is small. It may be that the lifetime of detectable civilizations is small. And because we do not know which term is the most fragile, every new discovery changes the emotional meaning of the silence. If we found simple life on Mars, or in the ocean of Europa, or in the plume chemistry of Enceladus, that would be one of the greatest scientific discoveries in history. But it would also shift the filter forward, because it would suggest that life begins easily when conditions allow. If microbial life is common, then the hard step is not the first spark, but something later. If we found independent, complex life elsewhere, the filter would move later still. If intelligence appeared multiple times independently, then the silence would press even more heavily on the question of technology and survival. This is the strange logic of hope and fear in astrobiology. Discovering that early steps are common is wonderful, but it can make later silence more ominous. The universe may be quiet because most planets never live, or because most living planets never think, or because most thinking planets never build technology, or because most technological planets do not remain stable and outwardly visible for very long. None of these options is proven. All are possibilities in a landscape of incomplete data. Yet the silence forces us to take them seriously, because the night sky is not crowded with obvious evidence of ancient galactic civilizations. We do not see confirmed galaxy-spanning engineering. We do not see unmistakable fleets of self-replicating probes. We do not receive a chorus of beacons from old stars. What we see is nature, immense and brilliant and largely indifferent, behaving according to physics. The great filter, therefore, asks us to look at ourselves with unusual sobriety. We are not merely observers of the paradox, we are inside it. Our existence is one of the data points. Our survival will become another. A civilization that understands the possibility of filters may be slightly better prepared to pass through them, because awareness turns blind risk into a subject of study. It encourages long-term thinking, global cooperation, careful governance of powerful technologies, protection of planetary systems, and a culture that treats endurance as a scientific and moral achievement rather than an automatic future. In this sense, the great filter is terrifying, but not paralyzing. It does not say that failure is inevitable. It says that survival may require maturity equal to power. It says that the silence above us might be the result of rare beginnings, rare minds, or rare wisdom. And as the earth turns quietly beneath the stars, with cities glowing on its night side and radio waves still leaking weakly into the dark, humanity occupies a narrow and extraordinary moment in the chain. Behind us lie billions of years of chemistry, cells, evolution, extinction, and chance. Ahead of us lies an unknown branch, a future where intelligence learns to last, or one where it becomes only a brief, bright interval in planetary history. The great filter is the name we give to that uncertainty, and it is so unsettling because it does not live among distant stars. It lives here, in the space between what we can do and what we can wisely endure, while the silent galaxy watches without telling us which side of the filter we are on. If the great filter imagines that civilizations may vanish before they become visible, the dark forest hypothesis asks us to consider a colder possibility. Perhaps some civilizations do survive. Perhaps the galaxy is not empty at all. Perhaps there are listeners scattered among the stars. But the reason the universe feels silent is that silence itself has become the safest language. The image is simple enough to enter the mind like a dream and remain there. A dark forest at night, every civilization a quiet hunter or a frightened traveler moving between trees, unable to know how many others are nearby, unable to know their intentions, unable to know whether a sound in the distance belongs to a friend, a stranger, or something far more dangerous. In such a forest, Calling out is not merely communication, it is exposure. A voice gives away position. A signal becomes a map. A greeting becomes a vulnerability. This idea is not a confirmed scientific theory, and it should never be treated as if astronomy has discovered a hostile galaxy. But it is a powerful strategic model because it turns the Fermi Paradox inside out. Instead of asking why no one is there, it asks whether everyone who lasts for a long time may learn not to announce themselves. The logic begins with uncertainty, and uncertainty, across interstellar distances, becomes unusually severe. On Earth, trust can form through repeated contact, facial expression, shared biology, slow negotiation, and the ability to correct misunderstandings quickly. But between stars, communication is delayed by years, centuries, or millennia. A message from a civilization 1,000 light-years away is not a conversation starter in the human sense. It is an artifact from their past, and any reply we send becomes an artifact for their future. If we receive a transmission, we cannot easily know whether the senders still exist, whether their society has changed, whether the message was deliberate or accidental, whether it came from a peaceful scientific group or a faction with motives no longer relevant, whether the signal represents a civilization weaker than ours, equal to ours, or so far beyond us that our categories fail. Game theory, when stretched across cosmic scale, does not provide a comforting answer. In a situation where the other player's intentions are unknown, their capabilities are unknown, their distance is large, and the cost of a mistake could be permanent, cautious strategies become mathematically attractive, even if no one is inherently malicious. The dark forest does not require every civilization to be evil. It only requires that civilizations cannot be certain others are safe, and that the consequences of revealing oneself might be irreversible. This is why the hypothesis feels so unsettling. It replaces monsters with ambiguity, and ambiguity can be enough to make rational actors quiet. A civilization that has survived for hundreds of thousands of years may have developed cultural memories, protocols, or philosophies shaped by deep caution. It may listen without transmitting. It may observe without interfering. It may compress its communications into narrow beams between its own worlds, reducing leakage into the wider galaxy. It may avoid building obvious megastructures, not because it lacks the ability, but because large signatures could attract attention. It may treat cosmic visibility as a resource to be managed carefully, like heat, energy, or risk. From our point of view, such a civilization would look almost the same as no civilization at all. A quiet galaxy and an empty galaxy can be observationally similar if our instruments are not sensitive enough to distinguish absence from concealment. This is the philosophical shadow behind SETI. Every telescope that hears nothing may be facing emptiness, or distance, or timing, or technological mismatch, or a culture that has chosen not to be heard. The human record of messaging the stars makes this question more intimate. In 1974, the Arecibo message was sent toward the globular cluster Messier 13, a beautiful mathematical postcard encoded in binary, describing numbers, DNA, a human figure, the solar system, and the telescope itself. The pioneer plaques carried diagrams of human bodies and a pulsar map pointing back toward Earth. The Voyager golden records carried music, greetings, images, and sounds of this planet: wind, birds, waves, heartbeat, footsteps, and the many textures of one young species trying to introduce itself to a future it could not imagine. These gestures were poetic, scientific, and deeply human. But they also reveal our assumption that being found is desirable. In the dark forest framing, that assumption becomes questionable, not because those particular artifacts are likely to bring danger across the vastness of space, since they are slow, small, and extraordinarily unlikely to be intercepted, but because they symbolize a larger debate about deliberate messaging. Should one group, one nation, one institution, or one generation have the authority to announce Earth's location on behalf of everyone who lives here and everyone who may live here after us? There is no settled global answer. Some researchers argue that deliberate messaging is a natural extension of exploration, and that any civilization advanced enough to threaten Earth could likely detect our biosphere, our atmospheric oxygen, our industrial traces, or our radio leakage without waiting for an invitation. Others argue that uncertainty alone justifies restraint, because a signal, once transmitted at light speed, cannot be recalled. Both positions are serious. Neither has the comfort of complete evidence. And this is why the dark forest remains so powerful as a thought experiment. It forces humanity to examine the ethics of cosmic speech before we know whether anyone is listening. It also connects to a broader point about detectability. A living planet like Earth has been visible as a biological anomaly for a long time because oxygen, methane, water vapor, and other atmospheric features can, under certain conditions, hint at life from afar. But a technological civilization can change its visibility rapidly. Artificial radio emissions may last only a short phase. City lights may be faint across interstellar distances. Industrial pollutants may be temporary or cleaned up. Heat waste may be reduced through efficiency. The most advanced civilizations may not look brighter, louder, or larger. They may look quieter, cooler, and more disciplined. This possibility challenges the Kardashev-style intuition that progress must always mean greater energy use and larger signatures. Perhaps some civilizations expand into visibility, but perhaps others mature into subtlety. Perhaps the ones that shout are young, and the ones that survive learn to whisper. Still, the dark forest hypothesis must be handled with restraint, because it can easily become more story than science. We do not have evidence that alien civilizations are hiding. We do not have evidence that the galaxy is hostile. We do not even have confirmed evidence that there is another technological civilization to hide from. What we have is a set of uncertain variables. Unknown frequency of life, unknown frequency of intelligence, unknown lifetime of civilizations, unknown risks of contact, unknown forms of technology, unknown motives beyond Earth. The dark forest is one possible arrangement of those variables, not the final answer. Its value is not that it proves the universe is dangerous. Its value is that it reveals how much of our optimism depends on assumptions we have never been able to test. It asks whether communication is always good, whether curiosity is always safe, whether intelligence naturally becomes cooperative at cosmic scales, whether long-lived civilizations would prefer openness or concealment, whether silence could be a sign not of death, but of policy. Under that lens, the night sky changes. The stars no longer appear only as distant suns. They become closed doors, each one glowing from the outside, each one perhaps empty, perhaps inhabited, perhaps listening through instruments older than human language. The Milky Way becomes not a battlefield, not a paradise, but a vast, uncertain ecology of information, where every signal has a direction, every detection has consequences, and every absence may have more than one meaning. For a sleepy mind drifting under this thought, the terror is not loud. It is not the terror of invasion or spectacle. It is the quiet pressure of not knowing whether our loneliness is real, or whether it is the shape taken by caution when stretched across 100,000 light years. Maybe no one is there. Maybe everyone is too far away. Maybe everyone has already passed through their loud youth and settled into silence. Or maybe, in the dark between the stars, wisdom and fear have become almost indistinguishable. And so Earth continues to glow softly, a blue world wrapped in cloud, leaking faint traces of chemistry, heat, radar, radio, and light into the surrounding dark, while our telescopes listen outward and our questions travel farther than our bodies ever have. If the universe is a forest, we are still at the edge of our small clearing, holding a candle, learning the difference between calling out and listening, between courage and care, between the desire to be known and the ancient instinct to survive. The silence may not mean the forest is empty. It may mean that every old civilization has learned how quietly a voice must move when the trees are full of stars. If the universe is silent because civilizations are rare, brief, hidden, or separated by impossible spans of time, then one of the most careful questions we can ask is not whether anyone is speaking, but whether anyone has changed the physical environment around them so dramatically that even silence would leave a shadow. A civilization does not need to send a greeting in order to be detected. It might warm its planet with industry, alter the chemistry of its atmosphere, illuminate the night side of its world, move asteroids, mine moons, build structures in orbit, or harvest energy on a scale so large that the starlight itself begins to look unnatural. This is the deeper idea behind the search for technosignatures, traces of technology that do not depend on conversation. Instead of waiting for a deliberate message, we look for consequences, for fingerprints, for places where nature's usual patterns appear slightly bent. In the 1960s, the Soviet astronomer Nikolai Kardashev proposed the way to classify civilizations by their energy use. And although the scale is simple, almost dreamlike in its boldness, it still shapes the imagination of SETI, because energy is one of the most universal languages in physics. A Type 1 civilization would use energy on the scale of its home planet, controlling or drawing from the major energy flows available there. A Type 2 civilization would use energy on the scale of its star. A Type 3 civilization would command energy across an entire galaxy. Humanity, by this measure, has not yet reached Type 1. We are still a young planetary species, powerful enough to alter our climate and send machines beyond the heliopause, but not powerful enough to manage the full energy budget of Earth with stability and wisdom. The strange appeal of the Kardashev scale is that it turns the Fermi Paradox into an observational test. If very old civilizations commonly climb toward Type 2 or Type 3 levels, then some of them might become visible, not by choice, but by thermodynamics. Energy cannot simply vanish. If a civilization captures the light of a star and uses it for work, the waste heat must go somewhere, usually radiated away in infrared wavelengths. This is why Freeman Dyson's famous idea of a star-enclosing energy system remains so important, even though the popular image of a solid shell is physically unrealistic. A more plausible version is a Dyson swarm, a vast collection of orbiting collectors, habitats, mirrors, or machines spread around a star, intercepting some fraction of its light and re-radiating heat. Such a structure, if large enough, might make a star look dimmer in visible light and brighter in infrared, like a lamp hidden inside a warm veil. The key point is not that anyone has found such a structure. They have not. The key point is that physics gives us a reason to search. Unlike radio messages, waste heat does not require aliens to be friendly, curious, or talkative. It only requires them to use energy. And so, astronomers have searched through infrared surveys, stellar catalogs, and galactic data, looking for sources that might be too warm, too dim, too oddly balanced between visible starlight and infrared glow. Most candidates dissolve under closer study into dust, young stars, debris disks, background confusion, or ordinary astrophysical processes. Dust is especially deceptive because dust naturally absorbs visible and ultraviolet light and re-radiates it as infrared, imitating part of what a technological structure might do. The universe is full of dust, and dust is a patient forger of signatures. This is one reason extraordinary claims move slowly in astronomy. The sky has many ways to be strange without being artificial. Tabby's star, officially known as KIC 8462852, or Boyajian's star, became famous because its light dipped in patterns that did not resemble ordinary planetary transits. A planet passing in front of its star produces a small, regular dimming, a repeatable shadow with a predictable orbit. But Tabby's star showed irregular dips, some unusually deep, and for a while, one speculative possibility captured public imagination. Perhaps we were seeing partial obstruction by alien megastructures, maybe something like a Dyson swarm under construction. It was an irresistible image, a distant star blinking not because of planets or dust, but because intelligence had begun to rearrange its light. Yet the deeper observations pulled the story back toward caution. Different wavelengths dimmed by different amounts, which is what dust-like material can do, while an opaque solid structure would block light more evenly across colors. The strongest current explanations involve natural material, perhaps dust or debris in unusual arrangements, though not every detail has been simple to model. Tabby's star remains fascinating, but not because it is evidence of alien engineering. It is fascinating because it teaches us how disciplined wonder must be. The first strange answer is not always the right answer, and in the search for cosmic intelligence, the sky will tempt us again and again with almost signals, almost patterns, almost shadows that fade into natural complexity when studied carefully. Then came Oumuamua, the first known interstellar object detected passing through our solar system, found in 2017 by the Pan-STARRS survey in Hawaii. It did not belong to the Sun. Its trajectory showed that it had entered from interstellar space, curved around our star, and was leaving again, a visitor not bound to our planetary family. It was small, faint, tumbling, reddish, and strange. Its brightness varied in a way that suggested an elongated or flattened shape, though the exact geometry remained uncertain because we never saw it up close. Most intriguingly, as it moved away from the sun, it showed a small, non-gravitational acceleration, as comets often do when sunlight warms ice and gas jets push them gently like tiny rockets. But Oumuamua did not display the obvious coma or tail expected from a typical active comet. This combination of features opened a scientific debate. Some researchers proposed unusual natural explanations: outgassing too faint to detect, hydrogen ice, nitrogen ice, a fragment of a Pluto-like body, a porous structure, or other forms of interstellar debris shaped by processes we had not yet observed directly. A small number of scientists suggested that radiation pressure on a thin object, perhaps even an artificial light sail, could explain the acceleration. That idea received enormous attention because it placed technology inside the unknown. But attention is not consensus. Most astronomers have treated Oumuamua as a natural interstellar object whose properties were difficult to constrain because we discovered it only as it was already leaving. The most scientifically honest sentence may be the quietest one. Oumuamua was unusual, and we do not have enough data to make it anything more than unusual. It is gone now, fading into the dark, carrying its answer away from us faster than our instruments could catch it. This is part of what makes these cases so hypnotic. They are not proof, but they are reminders that the boundary between the known and the unknown is not clean. A star dims strangely, and we must ask whether dust can explain it. A visitor accelerates strangely, and we must ask whether natural outgassing could be hidden. A galaxy glows in infrared, and we must ask whether dust, star formation, or black hole activity is enough. The search for technosignatures is therefore not a hunt for fantasy. It is a discipline of subtraction. We look for what nature commonly does, then for what nature rarely does, then for what nature has no good reason to do, and only at the very end, after ordinary explanations have been tested and weakened, does technology become a serious possibility. This hierarchy protects science from wishful thinking, but it also means that a true technosignature would have to survive an extraordinary gauntlet of skepticism. It would need to be repeatable or persistent, localized, physically coherent, difficult to explain naturally, and preferably detectable by multiple instruments in multiple ways. A radio signal would need to stand above interference. A laser pulse would need to repeat or fit a clear pattern. A Dyson-like heat signature would need to resist dust and astrophysical alternatives. An alien probe would need evidence stronger than odd motion. The silence of the universe is partly the result of this high standard, and that is a good thing. A lower standard would fill the cosmos with illusions. A higher standard leaves us with fewer stories but better truth. Still, the absence of confirmed evidence after decades of searching has meaning, even if that meaning is limited. It tells us that if Type 2 and Type 3 civilizations exist, they are not common in ways that are easy for our current surveys to detect. It tells us that obvious galaxy-scale engineering is not lighting up the sky in the simple forms once imagined. It tells us that the universe, at least through the instruments we have built so far, still looks overwhelmingly natural. But natural-looking is not identical to empty. A civilization might use less energy than Kardashev imagined. It might optimize efficiency, minimize waste heat, remain planetary, go digital, live under oceans, communicate with narrow beams, build small and subtle machines, or decide that expansion is unnecessary. It might leave signatures below our thresholds, or signatures in data archives we have not yet learned how to interpret. This is why Chapter 9 sits so close to the heart of the mystery. We have not merely listened for voices. We have looked for shadows on stars, warmth around suns, odd visitors in our own system, and patterns in cosmic light. We have found wonders, anomalies, puzzles, and lessons in humility. We have not found another civilization, and there is a strange calm in that result, because every failed candidate teaches us more about nature's ability to imitate meaning. Dust can look like architecture. Ice can look like propulsion. Stellar variability can look like intention. Noise can look like signal. The universe is not only silent, it is also capable of producing almost answers, and perhaps that is why the search feels so endless. Somewhere in the dark, if technology exists, it must be separated from the vast creativity of natural physics. Until then, Tabby's star keeps dimming in our memory, like a curtain of dust across a distant lamp. Oumuamua keeps passing through imagination, like a dark shard from another system, and the Kardashev scale remains a ladder drawn into the night, showing us how visible intelligence might become, while the stars themselves continue to offer no confirmed footprint, no unmistakable machine, no warm artificial shadow large enough to break the silence. If the silence of the universe has carried us through distance, time, planets, chemistry, intelligence, survival, caution, and the strange, almost signatures we have tried to read in the dark, then the final layer is not a new theory, but a different way of holding all the theories at once. Because perhaps the silence itself is the largest message we have received so far. Not a message with words, not a sentence sent by another mind, but a vast observational fact that forces every smaller answer to become more humble. We began with the simplest truth, that space is physically silent because sound requires a medium, and the vacuum between worlds offers no air for pressure waves to cross. But the deeper silence is electromagnetic, biological, historical, and philosophical. No confirmed radio beacon, no verified laser pulse, no unmistakable technosignature, no engineering mark so clear that the scientific community can say, without hesitation, that intelligence has appeared elsewhere. This does not mean the universe is empty. It means that within the narrow window of time, frequency, sensitivity, and method available to us, the cosmos has not yet produced a confirmed answer. That distinction matters because the history of astronomy is a history of replacing certainty with scale. Earth was once imagined as the center of everything. Then it became one planet around one star. Then the Sun became one star among hundreds of billions in the Milky Way. Then the Milky Way became one galaxy among vast cosmic structure. Then planets, once unknown beyond our solar system, became common enough that the question changed from whether worlds exist to what kinds of worlds they are. Each step made humanity smaller in position, but larger in understanding. The silence now performs a similar transformation. It does not simply shrink us, it asks us to understand what kind of smallness we inhabit. We may be small because we are one of many and have not yet found the others. We may be small because we are one of very few and do not yet grasp the rarity of our own existence. We may be small because the universe is so large that even many civilizations remain isolated by geometry and time. Or we may be small because intelligence, wherever it appears, is a brief local flame in a cosmos mostly governed by stars, gravity, gas, dust, radiation, and the slow cooling of matter. In every case, the silence teaches restraint. It tells us not to confuse expectation with evidence, not to mistake probability for observation, not to fill the dark with stories, merely because the human mind dislikes an unanswered sky. Yet it also tells us not to stop searching, because absence of evidence in a young search is not evidence of cosmic absence. Our instruments have barely begun their work. Radio SETI has sampled tiny portions of a vast search space. Optical SETI listens for flashes that could arrive in microseconds and vanish. Exoplanet spectroscopy is only beginning to explore the atmospheres of smaller worlds. Technosignature research is still learning how to separate artificial possibilities from dust, stellar activity, planetary debris, and natural chemistry. The space of possible signals is multidimensional. Sky position, frequency, bandwidth, polarization, timing, modulation, power, repetition, beam width, and interpretation. A civilization could be loud in a way we are not measuring, quiet in a way we mistake for absence, or present in archives where our algorithms have not yet learned the right pattern. This is why the silence should be treated not as a wall, but as a field of unknowns. It has structure. It contains limits. It narrows some possibilities and leaves others open. It makes obvious galaxy-spanning empires less likely in the forms we once imagined, but it does not rule out modest civilizations, hidden civilizations, brief civilizations, non-radio civilizations, ocean-bound intelligences, microbial biospheres, or life so different from Earth that our first instruments would walk past it like a person passing a sleeping city under fog. The great lesson is that the universe may not answer in the order our curiosity prefers. We may find life before intelligence. We may find atmospheric disequilibrium before a signal. We may find fossil chemistry on Mars, plume chemistry from icy moons, or oxygen and methane on a distant planet before we ever detect a deliberate transmission. We may learn that life is common and technology rare, or that planets are common but biology rare, or that intelligence is not the sort of thing that naturally becomes visible across interstellar distance. Each discovery will move the silence, reshape it, give it edges. For now, it surrounds us. But surrounding is not the same as defeating. A quiet night can still contain weather beyond the horizon. A dark ocean can still contain continents not yet mapped. The human task is to listen without arrogance and hope without surrendering rigor. This is where the silence becomes almost intimate, because it turns our gaze back toward Earth. In all the known universe, this small planet remains the only confirmed place where matter has become alive, where life has become aware, where awareness has built instruments capable of asking whether awareness exists elsewhere. That fact should not be used to declare humans the purpose of the cosmos, but neither should it be treated as ordinary in a careless way. A biosphere is not a background detail. It is a planetary achievement written over billions of years. Oceans holding chemistry, microbes altering atmosphere, tectonics recycling stone, sunlight feeding photosynthesis, extinctions opening new paths, nervous systems emerging from ancient survival, language carrying memory across generations, and science turning wonder into measurement. Against that history, our present technological moment is extremely young. We are not ancient cosmic judges, we are recent listeners. Our radio astronomy, our spacecraft, our planetary probes, our exoplanet catalogs, our search algorithms, even our language for these questions, all belong to the first breath of a civilization just becoming aware that the night is not only beautiful, but searchable. That youth is sobering, but it is also gentle. It means we do not have to force a final answer from an unfinished search. It means the silence can be lived with as an open problem, a scientific horizon rather than a verdict. Still, the emotional force remains. If we are alone, or nearly alone, then Earth is not just home, but a refuge of cosmic significance. And every forest, ocean, child, equation, song, and act of care becomes part of the only known voice the universe has produced. If we are not alone, but separated by distance, then the silence is a reminder that existence does not guarantee contact, and that other minds may be real, yet forever beyond conversation. If others are hiding, then the silence may be the shape of wisdom or fear, and humanity must decide how loudly it wishes to become visible. If civilizations tend to fade, then the silence becomes a challenge to last longer, to make intelligence not merely powerful, but durable. And if we are early, then the silence is not an ending, but a beginning. The stillness before a future galaxy slowly fills with life. None of these possibilities can be chosen by mood. They must be approached by evidence. But each gives the silence meaning, and perhaps that is the deepest reason it feels terrifying. It refuses to be one thing. It is loneliness, warning, humility, frontier, mirror, and invitation all at once. Above us, the Milky Way continues its slow rotation, carrying old stars, young stars, red dwarfs that may burn for trillions of years, dead stellar remnants, molecular clouds, rogue planets, icy moons, and worlds whose skies we have not yet imagined. The cosmic microwave background still cools as the universe expands. Gravitational waves pass through us from collisions long ago. Neutrinos stream through the planet almost untouched. Light from galaxies older than Earth slides quietly into mirrors built by a species that only recently learned to polish glass and write equations. Everything is speaking in the language of physics. And perhaps the first mistake was expecting the universe to speak quickly in ours. So the final answer is not that the universe is silent because it is empty, nor that it is silent because everyone is hiding, nor that it is silent because intelligence always fails. The honest answer is larger and more haunting. The universe is silent because every route from a distant world to a confirmed signal on Earth is narrow, fragile, delayed, and uncertain. And because we are still at the beginning of learning how to listen. That silence may one day break with a line of data, a repeating pulse, a chemical signature, a distant atmosphere out of balance, or a pattern in starlight that nature alone cannot explain. Or it may remain, century after century, until silence itself becomes the fact around which humanity builds its understanding of being alive. Either way, the message is already here. It is written in the absence of easy answers, in the patience required by science, in the small blue glow of Earth against the dark, and in the strange responsibility of a species that has heard no one else, yet keeps listening. For now, the universe does not answer. It waits. And in that waiting, it teaches us that to listen is not merely to expect a voice, but to become worthy of whatever truth the silence finally reveals. And so, for now, the universe remains silent. Not empty, not answered, but waiting. Maybe one day a signal will cross the dark and change everything we know. Until then, we keep listening. If this quiet journey helped you drift deeper into space, please like, subscribe, and join us again on Sleepy Space.